Hello. I will tell you about a small project in which we try to take quantum research challenges and transform them into computer games that will allow users of the internet to assist in solving these challenges. This basic concept builds on the concept of human computing, which tries to take small part of the resources that we spend now on playing computer games and spend them on something useful instead. And a prime example of this is the game of Folded, which is a protein folding game where users get to transform or perturb the side chains of proteins in order to find the minimum conformational energy. They have been immensely successful. They have more than 100,000 players, and the players have been able to invent new algorithms that can be applied to new proteins and find this minimum conformational energy. So it has been very successful in showing that people still have human skills of pattern recognition and intuition that can outcompete computers at certain tasks. So that's what we want to take into the quantum regime with our quantum games. So the idea is we have certain quantum games which will be based on quantum computers, atomtronics, quantum control and measurements, and optical lattices. And then in order to educate the players to most efficiently play, we have this quantum mechanics tutorial environment in which people will play predefined tutorial games, and then when they are well trained and understand the challenges, they can play the scientific challenges. In addition to that, we have a scientist developers interface, which is a little bit more nerdy, where research scientists can simulate their own ideas based on the time-dependent Schrödinger equation, the Gross-Petejevsky equation, or the Bose-Hubbard model. And the idea that we hope is that this graphical representation will enable the researchers to get new ideas. Some of these research ideas will then be solved conventionally, but some of them may also be posed as tasks for the online community to solve at our site, which is called Science. So the first quantum challenge that we've picked relates to quantum computers, and it relates to the optical lattice experiments that I helped set up in Munich, where we realized a mod insulator state and single site resolution of this. So where we have a crystalline structure of wells with exactly one atom in each well, like this here, and then we've managed to take a focused beam of light, send it onto a single site, and flip the spin from up to down. So in terms of the criteria that are listed here for a quantum computer, you can say that 2 of the 3 are met already now, and what remains is then the 2-qubit operation. And a couple of years ago, we sat down and tried to calculate what would be needed in order to transform this into a tweezer-based architecture. And you see here that we could remove atoms then and provide transport lanes, pick up an atom, transport it to another atom, and then merge those two on top of each other and let the control collisions realize the 2-qubit operation. So we computer optimized then the paths, and we were moderately successful, but we still believe that there can be more optimal path solutions, and that's what we want to use the quantum computer. So in the quantum computer game, the idea is that you have the atom represented in blue here, the wave function. You get to control the tweezer, the depth of the tweezer, and the position of the tweezer as a function of time. And the idea is to move it from the left side to the right side, and then delivering it here in the ground state of the potential, so that is with no sloshing in the end. In order for the players to practice, we have these slightly unphysical walls of death where players are supposed to manipulate and move around these walls. So here we see an example of a practice skill where you learn how to manipulate an atom, and the time-dependent Schrödinger equations is solved in real time as you play the game. And the idea is then to try to deliver it with minimal sloshing in the end. So when people have played this game for a little while, become proficient at moving atoms, they're ready for the scientific challenge. The scientific challenge here involved taking an atom on the left well, merging it with an atom on the right well in such a way that one atom stays in the ground state and the other one is mapped to the first excited state. And then the collisional interaction will then realize a square root swap gate. So here we see an example of a play which was not very optimal. There's still a lot of sloshing, and therefore the score is not very high, and that's what we hope that the players can improve on. So you may say that this was a little bit of a unphysical or unscientific way of optimizing, and then maybe this is more like it, because here you can see that the intensity of the tweezer as a function of time is displayed, and the position of the tweezer as a function of time, and then you can manipulate certain parts of the transport path, and the score is then updated live here on the bottom right. So that will allow you then to find out the positions in the motional path which are crucial, and then spend time optimizing there, very much like a computer algorithm would optimize the overall path in this way. So the idea is then that we hope that certain players are very good at playing the dynamic game and making very good initial guesses, where other players that are better at focusing on the small fine details can then play this game here, and then together they can find optimal solutions that are better than the computers have been. So that was the first game. I just want to briefly also introduce you to the second game environment that we have, which is the Bose-Hubbard model that simulates atoms in optical lattices. It's based on exact diagonalization. You can control the number of wells and the well population from 1 to 10, and you can control the interaction energy U over J as a function of time, and also the individual energy offset of the individual wells. So the first challenge in this environment is based on atomtronics in a tilted double well. So the challenge here consists in having n atoms on the left well, and then as quickly as possible transporting all of them to the right well. And here you see the energy diagram of this as a function of the tilt, and the fastest transport that you can realize is to jump to the first avoided crossing, wait for exactly one tunneling time, which will deliver one atom from the left well to the right well, and then jump to the next avoided crossing, where again another atom can tunnel across. So the problem with this approach here that we calculated a couple of months ago was that as you bring U down from very high values to realistic low values, then these individual avoided crossings start to overlap, which means that the nice beam splitters turn into higher dimensional beam splitters, and the dynamics becomes very complicated. And that's where we hope that the players can also participate in finding new. And so here you see an early version of the game here, where you can choose the number of sites. We have chosen 2, and then 3 atoms in the left well, and then you see here that you can control the tilt of the right well, and at a certain point you hit a magic tilt such that the energies are matched for single particle tunneling resonantly. Then you move to a new tilt, and again you move to a new tilt, and as soon as the 3 atoms are transported across, you move the tilt such that you block any tunneling. And in the upper right corner here you will see the wave function then transforming from the 0,3 component to the 3,0 component as a function of time, and we see a little bit of light blue here corresponding to a non-perfect transfer, and that's what the players can then optimize. So as a part of the education of the players and a part of an outreach program, we also go out into high schools and take over the education in classical mechanics, quantum mechanics, and try to teach them this based on small graphical illustrations, such as the ones illustrated here, measuring wave functions, illustrating stationary states, quantum tunneling, double slit experiments with pop-up questions, and so on. We also go to high school, to universities, take over the education for a little while, teach them about eigenspectrum and superposition states and time evolution of these states, wave packet scattering. And I think one of the most interesting parts is that we also have a simulation tool where you can define an arbitrary potential and then observe the time dynamics in this potential. And we've asked some students and also some researchers to spend a little bit of time programming their problem of choice, and it was very interesting to see what came out. Some people simulated triple well dynamics, Bloch oscillations, quantum random walks, Anderson localization, parametric heating. And in defining these potential, you can also define control parameters, and then you have this joystick-like control, which actually allows you to transform your illustration into a game that can be saved. So I just want to end with an illustration of the interdisciplinary nature of the research that we have here. We have partners from didactics, drama studies, psychology, anthropology, brain studies, and we all try to work together to solve different parts of scientific challenges within the different fields. And I just want to mention one particular challenge that I think is very interesting, and that is that of trying to find out more about how new ideas are generated in the brain. And in order to understand that, I just want to mention an old experiment conducted a couple of years ago, where the researchers made a small game of connected gears that could rotate. So it was just a line of gears, and then one rotated counterclockwise, and then the task was to find out what the last one, how the last one rotated. And they exposed this game to children, and the children tried to follow the motion of the gears with their finger in a way like this here, and then in the end they could see that the last one moved clockwise, for instance. So after playing the game for a little while, they suddenly realized that they could solve it in another way by simply counting A, B, A, B, A, B, and then they would exactly know what the last one, how the last one rotated. The interesting thing was that as they found this new algorithm, just before, their eyes did a random motion up and down and to the left and the right. So that was very interesting, and the researchers observed this and built a second part of the game, a second version of the game, in which at a random time suddenly a star would appear in the left corner, upper left corner, and then in the lower right corner, and then in the lower left corner. And after these stars appearing, the researchers found that there was actually a statistically enhancement of the probability of the players finding this global optimization algorithm. So that's a very interesting example of something going on in the brain, and then us actually stimulating that part of the brain and creating the environment for making new discoveries. And that's what we want to investigate also in the science at home, where there are certain theories that predict that the micromotion of the mouse reveals the state of mind of the player. So for instance, if you are intensely concentrated, then you may have a white noise spectrum, whereas if you are more relaxed, then you may have a 1/f spectrum in your mouse movement. What we want to do is then log the mouse movement as the players play, correlate the mouse spectrum with the success probability of certain challenges, and then when we know what the optimal strategy for solving challenges are, we can provide this as feedback to the players and tell them they were maybe too intensely concentrated or not concentrated enough based on their mouse movement. And in this way, we can actually assist them in solving challenges more efficiently. I think that's something that can be taken out to the society as a whole, and where we can apply if we can solve this. So I want to end with just our contact details, and thank you very much.